All right, chapter 9 starts with some sequences. And the first thing before we get to them is we're going to just talk about simplifying. So with these, we have these factorials. An n plus 1 factorial means you take n plus 1 times the next number below it. So if this, say n was like 8 plus 1 would be 9. You'd have 9 times 8, which was the n, times 7, which is 1 less than that, times 6, and so on, okay? If you have n factorial, that's n times 1 less times 2 less, and so on. These cancel, except for that n plus 1. And so we just get n plus 1 as the simplified version of that sequence. Okay? Not a factorial or anything else, it's just that. For this one here, we have 3 to the n, 3 to the n minus 2. We have 2 less 3's on the bottom than we do on the top, okay? So that means that once these 3's cancel all that they can, there'll be 2 3's left over. So you can either have that as 3 squared, or you can have it as 9. That's up to you, okay? And then as far as the n minus 2 factorial in this, again, n factorial would be n times n minus 1 times n minus 2, and so on. Well, this is n minus 2, n minus 3. It would pick up there, right? It would cancel. And then you would have this n times n minus 1 on the bottom. And then this would be our simplified. Again, there'd be 2 extra 3's on top and an n times n minus 1 on the bottom. For c sub n, right, we have this negative 1 to the n. It really doesn't do anything. It's not, there are no other numbers or anything like that, so we'll leave that. We have a certain number of x's on top and a certain number on the bottom. Notice how we have 2 less x's on the bottom than we do on the top. So that means we're going to have an x squared left over once things cancel. Again, these x's will cancel all but 2 of those x's there, and that's where we have that. So again, it can be a little confusing with those n's. If you get confused, throw a number in and see what happens. What's the relationship there, all right? And then as far as this goes, d sub n, if we were to take since these are the same exponent, we can go ahead and combine that and then simplify that fraction into a negative 1/2 to the n. The n squared really doesn't combine or do anything special, so we'll just leave it as that. And then that's our answer there. All right. So those are our simplified, and we'll be working on those as we go forward. But chapter 9 is sequences and series. And just to kind of get us kind of understand the difference here, sequences will be the terms themselves, the individual terms. So for example, I might have 1, 3, 5, 7, 9. That's a sequence. Okay, they're connected. There's a pattern that connects them all, but each of these are just the terms. I'm not doing anything with the sequence other than just kind of defining it. A series is when you add up a sequence. It's the sum of a sequence. Okay? So this would be if we took that and went 1 plus 3 plus 5 plus 7 plus 9 and added them up. That's the sum of the sequence. Okay? And that's the difference. Now, we won't get to series until later, so we're just going to start with sequences right now. Okay? And so if I give you a general term, I want you to be able to find certain things. Now this 1 here would really stand for what we traditionally call the first term of the sequence. All right? So if you were to put 1 in for n and go -1 to the first, that's -1. 3 plus -1 is 2. Okay? Then if I put 2 in, 3 plus 1 gives us 4, and then 2, and then 4. Okay? Now, the 0 term is often used to maybe create a sequence or a general term. So I'm putting it in here just to say that at times there might be a reason for us to consider what the term before the first term would have been. In this case, if we put 0 in, -1 to the 0 is 1. 3 plus 1 will give us 4. Okay? So that's what that sequence does. Right? Here, again, if I were to put 1 in, I would get 1 over 1 minus 2. I'd get 1 over negative 1, which is negative 1. Okay, if I were to put 2 in, I get 2 over 1 minus 4. I get negative 2/3. Right? If I put 3 in, I get negative 3/5. If I put 4 in, I get negative 4/7. Okay? If I were to put 0 in, I'm going to get 0. Again, I don't know if that would matter or not, but these are what we would say first term, second term, third term, fourth term there. Right. Let's do another one. If I put 1 in again, I'm going to get 1 over 2 minus 1, which is 1. If I put 2 in, I get 4 over 4 minus 1. I get 4/3. Put 3 in, I'm going to get 9 over 8 minus 1. I get 9/7. Put 4 in, I'm going to get 16 over 15. Okay, if you put 0 in, you get 0 over 0, which means there really is no 0 term for that. And again, I don't know if there would be a context for it or not. This is what we call a recursive sequence. What it's telling you is if you want any term, take the term before it. So this, d sub n minus 1, that stands for the previous term. And d sub n would be the next term. All right? And what this is suggesting, it's a real simple thing actually. It says take the previous term and add 5 to it, you'll get the next term. Okay? And so that's great, that's easy to use, except we need to know where to start, right? So let's say they started us at 2, okay? So to get to term, we just add 5, so 7, 12, 17. And if for some reason we wanted to come back to term 0, we would just subtract that 5 back, right? What would, and that's pretty easy to understand. All right, and then this last one here, if we would put 0 in for n, I get x to the 0, which is 1 over 1, so we get 1, okay? If we put 1 in, I get x to the first, which is x over 2. Put 2 in, I get x squared over 3. Put 3 in, I get x to the third over 4, and then x to the fourth over 5. All right, so those are my sequential terms there. All right, now what we're going to look at next is the limit of a sequence. And what we mean by that is what is going to happen if we let this keep going, all right? In other words, what happens to the terms if we keep going? All right. Are they going to keep getting bigger and bigger? All right. In other words, are they going to go to infinity? Are they going to get smaller and smaller? Are they heading to 0? Do they head to some other limit? You know, what's going to happen? We got to take a look at them. And what this is suggesting is whatever you use to find limits of functions, you're going to use the same thing to find limits of a sequence. So in other words, if you were looking at, say, 3x plus 2 over 2x minus 4, and we let x go to infinity, well, we know the degrees are the same, so the infinities are the same magnitude, and therefore this is going to head to a limit of 3/2, right? Well, so if I had 3n plus 2 over 2n minus 4, and I let n go to infinity, I let these terms go to infinity, well then that's also going to go to 3/2, right? That kind of makes sense that those would behave in the same way. So what we should do is we should go back and see if we can find the limits. And sometimes it's just using the same strategy we had there, and sometimes it's just using a little common sense. For example, here we saw that our terms went 4, 2, 4, 2, 4, 2, right? And it's certainly, that's how it's going to be forever and ever and ever and ever. So what is the limit as n goes to infinity of this sequence? There is none, right? It does not exist. In other words, the sequence oscillates between 2 and 4. It never stops going back and forth and back and forth and back and forth. So it has no limit. It has no value that it just settles down on. This one, however, all right? If we were to let n get bigger and bigger and bigger, you can see that the degree of n on the top is the same as the degree of the n on the bottom. And so these are going to gravitate to that ratio, which is a -1/2. Okay? And we could kind of see a little bit of that forming in the table when we did B sub n. Went from -1 to -2/3 to -3/5, that it was kind of heading in an area of -1/2 for sure. Okay? So that's that one. C, we have n squared over 2 to the n. Now this one might be a little trickier to see. If we took a calculator and kind of let this go, what you're going to see is these terms are going to get smaller and smaller and smaller until eventually they head towards a value of 0. So we could explore that on the calculator, and there's a notation on the calculator that lets you do this. In fact, I don't know if it's super important, but if you went to mode, there is a sequence mode right there. And when you go to y equal, this lets you put in it something in terms of a sequence. So when you hit your variable button, an n would pop up instead of your x that you're used to. Okay. Now again, I don't know how important this is, but this is, you know, where we go. We'll put it in the minimum n is 1, and then if we went to our table, all right, here's our n value, and here are the sequence terms. That's the 4/3 that we had before and all these other ones. Now you can see as I let n get bigger and bigger and bigger, these terms are getting smaller and smaller and smaller. They're heading to a value of 0, like we suggested. And so one way that you can prove that by using like L'Hopital's rule is that if we had x squared over 2 to the x, and did the derivative, you know, again, that's infinity over infinity to start with, but if you take the derivative of the top, take the derivative of the bottom, we haven't talked about this, but an exponential function, just like e to the x repeats, anything else also repeats. It has a little extra with it, but that extra isn't going to change anything. This is still going infinity over infinity, so you do L'Hopital one more time, and we'll have natural log 2 squared 2 to the x. Now that the bottom is still going to infinity, but the top has stopped. This will go to 0 then. Here we started with 2, and we keep adding 5 and adding 5. So again, we don't need any special rule or thing like that. It's pretty obvious that that's just going to go off to infinity there. Okay. Then we have our last one, this x to the n over n plus 1. And the top is going x squared, the bottom went 3. And then we have x to the 3rd over 4, x to the 4 over 5. All right, now, initially we could feel like, okay, this is probably going to head to infinity, like x to some power is probably bigger than that number. But again, that's an assumption. It depends on x, right? Because, for example, if x was 1/2, all right, then 1/2 squared, which is 1/4, and then 1/2 third is 1/8. Well, these terms are getting smaller, right? Significantly smaller. So if x was 1/2, this actually would get smaller and smaller. This would head to 0, all right? So here's the deal. If x is, and we'll go absolute value of x, is less than 1. So in other words, if x is between -1 and 1, it's a fraction that when you multiply it gets smaller and smaller and smaller and smaller. If it's there, this is going to go to 0. But if the absolute value of x is greater than or equal to 1, well, now the terms get bigger and bigger and bigger and bigger, or they stay 1 over n, which actually I would say this is probably truer. Forgive me on that mistake. But if it's bigger than 1, then the terms are going to get bigger and bigger and bigger and bigger, and then this will go to infinity. So again, in other words, if x is greater than 1 or if x is less than -1, then that would go off to infinity or to negative infinity, whichever the case may be. All right, so let's try a fresh one here. Now we've added two different things here. This is what we call an alternator, meaning that this is going to make our terms go positive, negative, positive, negative, positive, negative. And then we have our factorial that we've talked about before already. But that means we're going to take whatever number we put in, we'll multiply that number by everything before it as well. So if we put 0 in, negative 1 to the 0 is 1. 1 over 0 factorial is also 1. And 0 factorial really doesn't make a whole lot of sense. It is equal to 1 by definition. We need it to work that way in math, and so that's the way it is. All right. If I put 1 in, get negative 1 over 1, which is negative 1. If we put 2 in, we get positive 1 over 1/2. We'll get positive 1/2 there. Put 3 in, we'll get negative 1/6. Put 4 in, we get positive 1/24. Okay. Again, it's pretty clear to see that this sequence is heading to 0. These terms are getting smaller and smaller pretty quickly, and that's what's happening there. Okay. So if I want to do the first 5 terms of this sequence, put 1 in, I get 3 over 1. Put 2 in, I get 9 over 2. Put 3 in, I get 27 over 6. Put 4 in, 81 over 24. Put 5 in, I get 243 over 120. Now it's important to not judge a sequence by the first couple terms, right? We went from 3 to 4.5, and this is also 4.5. Might make you feel like it's getting bigger, but once we get past 3, the bottom is going to start growing significantly faster, which makes sense, right? Like this was 3 over 1. Then we did 3 times 3 over 1 times 2. Then we did 3 times 3 times 3 over 1 times 2 times 3. That's why these are the same. We got multiplied by that. But when we get here, we multiply the top by another 3, but now we multiply the bottom by 4. Then we get here, we multiply the top by 3, but multiply the bottom by 5. So as we go forward, what we multiply the bottom by is bigger than what we multiply the top. That's why these terms are going to get smaller and smaller and smaller. It's going to head to 0. Now this gives us a little rule here that helps us understand the combination. These factorials are significantly faster growers than anything else. A factorial expression will always beat an exponential, which is what we were dealing with there. But an exponential, as we learned last week, is going to always outpace a polynomial. This is the magical relationship that we want to kind of get straight here, okay? And as far as that exponential goes, I'm going to write this, and it'll make more sense as we go into section 9.2, that we're talking about exponential equations that do grow, where the r value is greater than 1, not ones that get smaller and smaller. That's a whole different story. Okay? All right, the last thing we're going to talk about here is creating an nth term for a sequence. And what we mean by that is if I were to put 1 in, put 2 in, put 3 in, like this, what would be an expression that if I put 1, 2, 3, 4, I'd get 2, 4, 8, 16, 32 on the top, and 1, 3, 5, 7, 9 on the bottom. Now, that means that we're really talking about 2 different things. So you can kind of just ignore the relationship. Just look at the top and say, what do I have to put 1, 2, 3, 4, 5 in to get those things? And that's 2 to the n. 2 to the first, 2 to the second, 2 to the third, and so on. As far as the bottom, we're adding 2 to get from term to term to term, so that's going to be 2 times n to start with. And if I were to put 1 into that, or 2 into that, or 3 into that, I would get 2, 4, 6, 8, 10. I would just need to subtract 1 from that to get to those terms there. All right? And then this would be our expression. On this one here, you can see that we have an alternator that's part of this. So we're going to include that alternator. Now, the one thing when you do the alternator is you have to see, is it on the same system? In other words, if I were to put 1 in here, if I start with n, if I put 1 in, do I get what I want? okay? In this case, I do. If I put 1 in, I get negative. If I put 2 in, I get positive. But sometimes that can be off by 1. And if it ever is off by 1, you would just either do a +1 or a -1 to put it onto the right cycle, okay? So that takes care of that. And then we've got a sequence on top, 2, 8, 26, 80, 242. And this one's really tough. If you add 1 to each of those, you get something a little more familiar. Okay, this is 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. In other words, that's 3 to the n, but we've taken 3 to the n and we've subtracted 1 from it. That's a pretty tricky one. The bottom's a little more familiar. We have 1, then we have 2 times 1, then we have 3 times 2 times 1, 4 times 3 times 2 times 1, 5 times 4 times 3 times 2 times 1. That's n factorial. And then that would be our thing. This factorial, we're going to become much more familiar, and when we see it, we'll be able to do it right away. All right. So that gives you a little idea of what we were doing in this section here.